the air was poison. Then we made it bread. Of all the things a plant needs to grow, the one it craves most and can least easily find is nitrogen. This is one of the great paradoxes of the living world. The air above every field is, by volume, very nearly 4/5 nitrogen gas and almost limitless ocean of it pressing down on the soil. And yet for nearly the whole of agricultural history, crops starved for want of it, because the nitrogen in the atmosphere is locked up in a form that life cannot use. The two nitrogen atoms in a molecule of nitrogen gas are bound together by one of the strongest chemical bonds in nature, a triple bond so stable that the molecule simply drifts through the world, inert, refusing to react with almost anything. A wheat plant standing in a field is, in effect, surrounded by a feast it cannot eat. To grow, it needs nitrogen in a fixed form, combined with hydrogen or oxygen into compounds like ammonia or nitrate, and producing that fixed nitrogen was, until just over a century ago, one of the genuine bottlenecks on human survival. For thousands of years, farmers managed this scarcity without understanding the chemistry behind it. They learned, by patient trial and inheritance, the practices that quietly return nitrogen to the soil. They spread animal manure, which is rich in it. They let fields lie fallow so that natural processes could slowly replenish them. And, most cleverly of all, they planted legumes, peas, beans, clover in rotation, without knowing that the roots of these plants host colonies of bacteria able to perform the one trick nothing else on the farm could, pulling nitrogen out of the air and fixing it into the soil. These were real and effective methods, but they were also a ceiling. They could only return so much nitrogen, so fast. The amount of food a society could grow was capped, ultimately, by the amount of fixed nitrogen it could gather, and that cap held human population in check for millennia. By the late 19th century, as European populations swelled, scientists began to speak with real alarm about a coming nitrogen famine, a future in which there would simply not be enough fixed nitrogen in the world to feed everyone. For a few decades, the world found a temporary escape in two natural deposits, and the lengths people went to for them reveal just how precious fixed nitrogen had become. The first was guano, the accumulated droppings of seabirds, piled meters deep over centuries on rainless islands off the coast of Peru. It was extraordinarily rich in nitrogen, and through the middle of the 19th century it was dug out, bagged, and shipped around the world in enormous quantities, the foundation of a global trade in more than one diplomatic crisis. The second source was sodium nitrate, or saltpetre, mined from the bone-dry Atacama Desert in South America. So valuable were these deposits that nations went to war over them. The War of the Pacific in the early 1880s was fought, in large part, over who would control the nitrate fields. A substance scraped from desert and dug from bird droppings had become worth fighting and dying for. But everyone understood these were finite. The Guano Islands were being stripped bare, the nitrate would not last forever, and the underlying problem remained: humanity needed a way to make fixed nitrogen for itself, from the inexhaustible supply in the air, rather than mining the dwindling gifts of the past. The breakthrough came in Germany in the first years of the 20th century, and it was a triumph of sheer chemical stubbornness. A chemist named Fritz Haber set out to do what nature did so reluctantly: force nitrogen and hydrogen to combine into ammonia. The obstacle was that stubborn triple bond. To break it, Haber found he needed extreme conditions, temperatures of several hundred degrees, pressures hundreds of times that of the atmosphere, and a catalyst, a special metal surface that would coax the reluctant molecules into reacting. In 1909 he demonstrated a small tabletop apparatus that dripped out liquid ammonia, made from nothing but air, hydrogen, and energy. It was a few drops, but it was proof. The harder task, turning a delicate laboratory demonstration into something that could run continuously, at industrial scale, inside reactors that could survive those crushing pressures and temperatures day after day, fell to an engineer named Carl Bosch, working for the chemical firm BASF. The problem he solved was as much about metallurgy and plumbing as chemistry: building vessels that would not burst or weaken, finding cheaper catalysts, scaling everything up by a factor of thousands. Within a few years, the Haber-Bosch process, as it came to be known, was producing fixed nitrogen by the ton. Here is the fact worth carrying away from all of this, the one to mention at the dinner table. It is now estimated that the Haber-Bosch process is responsible, directly or indirectly, for feeding around half of all the people alive on Earth. Roughly half. The synthetic fertilizer made from atmospheric nitrogen is what allows farmland to produce the yields that sustain a population of 8 billion, when the natural nitrogen cycle could support perhaps half that. Scientists have even traced this in our own bodies. A large fraction of the nitrogen atoms in your tissues, in your muscles, your skin, the proteins that make you passed at some point through a Haber-Bosch reactor, pulled from the air in a factory before they entered the food chain and, eventually, you. It is a genuinely strange thought. The air you breathe and the substance of your body are connected by a steel vessel in a chemical plant. A quiet industrial reaction, invisible and almost entirely unremembered by the public, is one of the load-bearing pillars of modern human existence. Take it away, and within a year or two, by most estimates, a large part of humanity could not be fed. No honest account of this can leave out its shadow, because the same chemistry that feeds the world has a darker register, and the two are inseparable. Fixed nitrogen is the basis not only of fertilizer but of explosives. The very ammonia and nitrates that make plants grow also make munitions, and the timing was grim. The Haber-Bosch process matured just as the First World War began. Germany, cut off by naval blockade from the South American nitrate it would otherwise have needed for explosives, was able to keep fighting in large part because it could now manufacture nitrogen compounds at home, from the air. The same discovery that would go on to save billions from hunger also, in its first years, prolonged a catastrophe. Fritz Haber himself embodied this contradiction more painfully than anyone. Celebrated for the bread from air that would feed the world, he also directed the development of chemical weapons, becoming a central figure in the introduction of poison gas to the battlefield. He received a Nobel Prize and lasting infamy from the same body of work. It is a reminder that the small hinges on which history swings do not always swing in one direction, and that the most consequential discoveries are rarely simple in their meaning. And yet, set beside the long sweep of what came after, the dominant legacy of that reaction is the food. Walk past any field of wheat or maize or rice anywhere in the world, and the green abundance of it almost certainly owes part of its existence to nitrogen drawn from the air in a factory. The fields look timeless, eternal, the way farmland always has, but the yields they produce are a thoroughly modern phenomenon, resting on a chemical process barely 100 years old. It is the perfect example of a small hinge, an obscure industrial reaction, understood by almost no one outside chemistry, with no monument and no place in the popular memory, quietly holding up the food supply of half the planet. The great visible doors of history, the rise and fall of nations, the growth of cities, the population explosion of the 20th century, all swing, in part, on this nearly invisible hinge, the moment two German scientists worked out how to make bread from air. The next time you eat, it is worth a passing thought that the nitrogen building your body may once have been a breath of the open sky, pulled down to earth and fixed into food by one of the quietest and most important reactions ever devised. There is a quiet humility in the thought, too, that for all our cities and machines, the thing keeping most of us alive is still, at bottom, the growing of plants in soil, and that the single change which let those plants feed billions more was not a grand visible monument but a reaction running silently inside a steel tank, turning the empty air into the stuff of life.